We're going to talk today about negative emissions and a few other things. To remain below 2 degrees centigrade by 2100, most projections argue that the world will need to find a way to achieve negative emissions in addition to cutting back substantially on emissions from all the various economic activities that take place around the world. Actually, the national academies have run 3 consensus studies in this general area. Jennifer Wilcox, who we'll hear from in a few minutes, was a key author of the study on the left. I was also a member of that panel. And then there was a specific study a few years later on negative emissions, and also relevant, but not really about negative emissions, is a recent consensus report from the academies on carbon dioxide utilization markets and infrastructure. Here are the strategies that were explored in the Academy study on negative emissions. Jennifer's going to make some passing comments to some of them, so I wanted you just to at least know that they'll be in the slides when they're distributed. And the report has also estimated the current costs and capabilities of each of those strategies. Jennifer is on the faculty at the University of Pennsylvania, but she's on leave now serving in the U.S. Department of Energy. And because we were concerned that the U.S. government might be shutting down, we instead arranged for her to record a video, and which she will, and we'll play that now, and then we'll have 3 live remarks, and I will wrap up with a final set of comments at the end. So,
hello, thank you for having me today, and apologies that I can't be there in person. Excited to talk to you about carbon dioxide removal and also the work that we're doing at Department of Energy. I wanted to start out with looking at what is the role of carbon removal in achieving net zero greenhouse gas emissions. So, as you know, the United States in the Biden-Harris administration set a number of climate goals, one being achieving net zero greenhouse gas emissions by mid-century. And so the question is, what are the different actions that we need to take in order to reach net zero by mid-century? And what is the role of carbon dioxide removal in achieving net zero? And so highlighting in red some of the carbon management aspects of the portfolio, and more specifically to think about carbon removal and its role, recognizing that there's going to be emissions that are truly, truly hard to decarbonize, and that carbon removal is going to be a strategy for us to achieve net zero by counterbalancing those truly hard to remove emissions. The other piece that's important to recognize is that when we think about carbon management or point source capture from individual emission sources, and we think about engineered approaches to removal, like direct air capture, that the overlap is that we have to somehow also manage the CO2 downstream. And the method of dealing with that scales with the size of the emissions on the order of gigatons is really geologic storage of CO2. And so there is a little bit of overlap in regards to downstream management of CO2 when it comes to methods that are avoiding emissions from entering the atmosphere and methods that are removing CO2 from the accumulated pool in the atmosphere. A good resource is the CDR primer, which a group of 40 researchers from North America and also across Europe published back in 2021. And in chapter 1, we have this image that's showing it's really about responsible way of thinking about carbon removal, not being there to allow us to overshoot, not being there to simply offset emissions that we have technologies to decarbonize today, but really being there in a responsible way of thinking about counterbalancing hard to decarbonize sectors. And so this should never be seen as a means to continue emitting at the rate that we're emitting today. We still need to, in parallel, advance and rapidly advance deep decarbonization methods in addition to scaling up CDR. At the end of the day, we're still going to need on the order of gigatons of CDR. We're on the scale of, say, thousands of CDR removed, if you think about kind of engineered approaches. And we need to somehow increase that by 6 zeros in less than 30 years. And so if we don't start today, we'll never have this tool in time. And also in Office of Fossil Energy and Carbon Management at the Department of Energy in April 2022, we published our strategic vision. And this is an image from that publication. And so what we're showing here is on the right-hand side is doing that bottom-up calculation to understand what are the emissions that truly are difficult to decarbonize. And when you think about the United States emissions, it's on average about 6 gigatons of CO2 each year, and distributed in different sectors. These are the sectors that are truly hard to decarbonize. So when we think about agricultural sectors and in methane emissions or N2O emissions from agriculture, when we think about long-haul trucking and you think about aviation where biofuels are only going to play a portion of that, and shipping as well, and also residual emissions. If we're looking at the power sector and our methods are capturing 95% CO2, there's that 5% that's going to be emitted. We look at supply chain leakage and emissions associated with oil and gas production and methane. Even if it's leak tight, there's going to be residual emissions. And when you add all of this up, it adds up to about just roughly a gigaton of CO2. And so we have to scale up to the gigaton scale no matter what. And it's a portfolio of solutions, and we kind of list those on the left-hand side, from biological approaches to CDR to chemical approaches, mineral approaches, and also ocean CDR. And so I'm going to talk a little bit about the efforts at Department of Energy. We're investing broadly across this space. And so I had the opportunity to be on the committees of 2 National Academy of Sciences reports, one on what we call climate intervention, trying to replace the term geoengineering, which we, really consider geoengineering as being like the other knob that one can turn, so changing the reflectivity of the Earth, where carbon removal is quite different, and the impacts of turning each of those knobs is quite different. And so we wanted to kind of come up with a broader term that was inclusive of both. So we came up with climate intervention. In this, we really just kind of laid out what each of the approaches are, what the potential impacts could be. And then we followed up with another report that really was a blueprint for the government of there are these different approaches, and how can we invest in kind of first of a kind, and what technologies across the entire portfolio, and really assigning responsibilities across the US government, from the Department of Energy to EPA to, all of the different aspects. And so when I started in January, just day one of the administration as a political appointee, I took that blueprint and really thought about, how can we invest? And so we had a number of Earthshot initiatives in the Department of Energy, and one is specifically on the carbon negative shot. And so here we're investing in the entire portfolio, from oceans to coastal blue carbon to looking at accelerating chemical weathering of rocks, engineered approaches like direct air capture, biological approaches like improved forest management, increasing carbon storage in soils, and really just looking at the entire portfolio. The goal at the end of the day is how can we invest such that we can get from thousands of tons of durable carbon storage today to millions of tons over the next decade. And if we make those investments, can we bring down the cost point down to $100 per net metric ton of CO2? And so really investing in all of these approaches, and this is a joint effort through broadly Department of Energy, my office, but also ARPA-E, energy efficiency and renewable energies, and just really a concerted effort to look at how can we, many of us are focusing on the technical aspects of carbon removal and thinking about the price point, the cost of it being quite high. and thinking about the nature-based as being just a little bit, not as costly. But at the end of the day, if we have to also develop the hardware, the sensing, the measurement technologies that are coupled to those nature-based approaches, it's still a question of how much that will cost when you couple the nature-based approaches to the quantification devices that are required to have monitoring, reporting, and verification. And so that we can start to actually compare the impact of these approaches on some kind of level playing field. And so a lot of the work that we're doing at DOE is investing in that hardware, the technologies, so that a soils project for agriculture and a forest project, those applicants at the end of the day, those stakeholders will have the tools available to be able to quantify the additional carbon that's removed. And so all of these projects are kind of at different stages in terms of the broader portfolio. We have the opportunity in the United States through the bipartisan infrastructure law, which is $12 billion across all carbon management over the next 5 years, including a significant amount of money for the first of a kind direct air capture hubs. And I'll talk a little bit about that in a moment. We also have the Inflation Reduction Act, which is really the tax credits. And we have 45Q. In this case, what that's doing is just, it's additive. And so if you have a first of a kind demonstration funded through the bipartisan infrastructure law, and the government's paying up to 50% of the capital investment of that project, you can also stack with it the Inflation Reduction Act 45Q credits, which is $180 per ton of CO2 for direct air capture. And we've also reduced the minimum project size through this is to 1,000 tons of CO2 durably removed. And we just made an announcement recently where we have roughly $100 million that we're investing in concept studies through front-end engineering design studies through a number of different technological approaches or engineered approaches to direct air capture, and funded first of a kind 2 hub projects as well. And that's $1.2 billion. So $100 million for the concept studies and the feed studies, and 1.2 for the direct air capture hubs. And the goal for those direct air capture hubs is to scale up to 1 million tons of CO2 removal per year. At the end of the day, Congress is asking us to fund 4 at a total of $3.5 billion. And so when you look at the selections made for concept through front-end engineering design, you can see that they span across the United States, which is really exciting, and also span different types of technologies. And so we're looking at approaches that are strictly, where 100% electrons are fed into the process. We're looking at approaches where it's a combination of heat and power, so thermal energy, electric energy going into processes. And it also depends on, as you design a technology, you're thinking about siting it. It depends on what are the low carbon energy resources regionally available to you. Do you have stranded electrons? Do you have thermal energy? And what is the quality of heat of that energy? Some of the approaches require 1,000 degrees C in order to regenerate the material to produce a high purity stream of CO2. Some more of the solid sorbent-based technologies only require 100 degrees C heat. And so couple well, for instance, with geothermal, where you're not having to choose between energy production or direct air capture, you can actually co-optimize both. And so looking at a variety of energy resources combined with different technologies all across the United States, and really from the concept all the way through the front-end engineering design, which is the first step before actually carrying out a demonstration. And so really what we're trying to do with these investments is meet industry where they're at today, meet the technologies where they're at, so that we can have a robust pipeline, so that when we go to fund the next 2 direct air capture demonstrations, we have a broad portfolio to choose from. And so this is a little bit more detail about the 2 direct air capture hub projects that we're investing in. One is the technology provider's carbon engineering, and the other one is Climeworks. And so one is a liquid solvent. Carbon engineering is a liquid solvent-based approach. Where at the end of the day, they're producing a carbonate material that they have to really heat to high temperatures in order to regenerate. And Climeworks is using an amine based solid sorbent and can use a lower quality of heat. Both have pros and cons, of course, and one is sited in Louisiana and the other one in Texas. The other thing that's important to mention about this is they have to have that CO2 offtake. And so each of these projects is coupled to CO2 sequestration, and that's an important concept too that I mentioned earlier. And so dedicated carbon storage, and that is in collaboration, DOE, with the Environmental Protection Agency that works to permit the Class 6 wells for deep CO2 injection. And so with that, I want to just briefly mention our Carbon Safe program. And so this walks folks through the different processes. If they have formations for deep CO2 injection, we start with funding just the characterization of the reservoir to be able to understand whether or not it's suitable for deep injection of CO2. And then phase 2 is the complex feasibility, characterization and permitting. And finally, phase 4 is the construction of the well and the Class 6 permit. And so we have this in place. We have, through the bipartisan infrastructure law, $2.5 billion to invest over the next 5 years and to build out the capacity of 65 million tons of CO2 injection per year across the United States. And we've started to fund projects already at the different phases that you can see here on the map. And so it's pretty exciting that we're starting to just really build out the capacity, which is really the offtake of CO2. And as I mentioned, is critical for the engineered-based approaches to carbon removals to have that downstream carbon management. We're also investing, of course, as I mentioned, through the carbon negative shot, through base appropriations, also looking at ocean carbon removal. We have 8 projects that we're funding so far, really at the early stages, and focused on abiotic ocean-based carbon removal. So thinking about alkalinity enhancement of oceans, being able to understand too if there can be regional impacts associated with reducing ocean acidification. And then we're also looking at direct air capture coupled to products. And in this case, these are at best neutral, not considered carbon removal, since you're then combusting oftentimes or using the chemicals or fuels and re-emitting the CO2 in the atmosphere. But if the hydrogen source is biomass, and in your production of the hydrogen, you are storing the carbon that's deep underground that's produced, and that hydrogen has a negative carbon intensity associated with it, there is the possibility of making chemicals and fuels that are carbon negative if the hydrogen has a carbon negative footprint and the CO2 is sourced from the air. And so that's pretty interesting too. And with that, thank you so much again for having me virtually, and wish I could be there and enjoy the rest of the workshop. Thank you.
Microphone.
Since Jennifer said a fair number of things about deep geologic sequestration, I wanted just to take 3 minutes before we move on to the other parts of this session. Some years ago, a number of us figured out that at least in the US, where ownership of the deep subsurface is not state controlled, but is essentially different state to state, that the US needed a coherent approach to managing sequestration in the deep geology. And we ran a fairly large project involving not just technical people, but lawyers and regulatory people, and produced, actually at the end of the document, a 50-page draft bill, not with the sense that anybody on the Hill was going to actually pick it up and pass it, but that it would at least, be grist for cutting and pasting to do something. But decarbonization wasn't high on the political agenda a decade ago, so nothing much happened. And instead, under the authority to protect groundwater, EPA developed rules for something called Class 6 injection wells that Jennifer mentioned. And the result's an awkward state-by-state system that, while it's better than nothing, doesn't systematically address key issues such as liability and long-term stewardship. Approval of new wells has been very slow. Since the Class 6 rule was promulgated in 2010, the US EPA has approved only 6 permits, although there are a number more in the pipelines. And with a doctoral student named Emmy Moore and Valerie down here at the other end of the table, we've just completed a study of how long it's likely to take to develop, permit, and start operations for a sequestration well. I'm going to show you just a couple of slides to give you that answer. The way we've done this is by identifying 6 clearance points that one needs to get through in order to get to the point of developing a well. And then for each of those clearance points, Emmy has elicited probability distributions from 3 experts. So here are box plots showing the amount of time these experts thought it would take to get past each clearance point. You can see that there's not great consensus about some of them. And then you do a stochastic simulation in order to estimate the overall time to completion. And you find that there's a 95% chance that it's going to take at least 5 years. There's a 5% chance it could take well over 10 years. The U.S. is talking about decarbonizing the electricity system by 2035. This is a serious problem. And so one of the things we are working on now is trying to figure out some strategies that could safely speed the process. I won't read them since time is short. But we can move on now to the first presentation by Gideon Friedman from the Ministry of Energy and Infrastructure at Jerusalem, Israel.
The Chief Scientist Unit has several roles. We basically see ourselves as leading innovation in both in the technical sense, but also in let's say procedural sense, innovating procedures. So we are part of the ministry, let's say long-term policy setting group. Also midterm, we participated in the 2030 plan for the ministry for going into renewable energy primarily and emission reductions for 2050. We are pushing innovation in the energy and water markets. We are supporting, as I said, we are a funding agency, so we are supporting entrepreneurship from academic research through early stage startups and pilots and demonstration. So we have essentially 3 main support programs for these 2 steps along the R&D process. And we are trying to improve the procedures for innovation and trying to remove obstacles where possible and invent new procedures that are hopefully easier. I do want to emphasize the importance of investing in R&D because sometimes it's not so clear, certainly from our perspective in the government. We have to work very hard to get the funds. And I hope that the participants in this conference who are mostly getting the grants, and so I basically want to show my appreciation for your work and every unit of investment that we put in R&D. This is the research, or actually 2 researches that were done in Israel for how much each unit of investment actually increases the GDP later on. So we get, for investment in high tech, we would get between 4.7 and 5.5 on the left-hand side units of increased GDP. And generally, the energy market is considered to be mixed traditional because it's infrastructure field. Although I believe we are moving more and more toward the mixed high tech type of things as the digitalization is penetrating more and more even this infrastructure field. So it's every dollar that's invested in R&D is really beneficial. As an example for our own investments, I point out 2 numbers. So if we invested in the industrial sector, industrial R&D, about 200 million shekels over the 8 years between 2012 and 2020, follow-up private investment in some of the companies that we supported in earlier stages, summed up to about 2.4 billion shekels, which is a factor of 12 to our investment, and it's very impressive. And another way to measure that I tried last year, I said, okay, let's do it year by year. I said, okay, well, how much did we invest in 2022? We invested about 170 million shekels in R&D in total, not only industrial, also academic. And again, what was the private investment during that year alone in companies, mostly companies that we invested in the past, and for that specific year only, it was 586 million shekels. So it's a factor of 5 on that. So I believe our investment is very effective. These are logos of companies that were able to go for an IPO, and we invested in the past in them. I would say that this field of energy and water, the infrastructure field, it's very difficult to get private funding for the reasons that I show here mostly. One thing is it takes a very, very long time to get from the idea stage to an actual product. 10 years and more, we see even more, 12 and 15 years from the stage of the idea to actual product. Very long time, which most investors will not consider reasonable. In many cases, the investment is very high at the later stages in the proof, the field proof of the technology, where actual big infrastructure is required. The investment is very high, and the risk is still not negligible. So it's difficult to get private money there. And finally, the return on investment is quite low because this is a regulated area, and generally the margins in this in energy and water are not so high, so it's not possible to make a big return. And also the situation of winner takes it all does not actually exist, like in high tech sometimes happens, because most countries want their infrastructure to be with at least a national color. So a foreign company with the technology cannot own the facilities by itself. So again, this is a deterrent to investors. That's why government has to step in and intervene. I would say this is a distribution of how we, in the last 2 years, split our funding between academic research and the rest. We see that most of the investment goes to academic research and pilots. I said pilots are expensive in this area, and we also, and the academic investment that we do are high. We really believe that we have to put almost most of the money in the academic research, because that's where the innovation, the basic innovation comes from, and it's all deep innovation. I mean, the technology is deep, requires deep research. It's not an idea that someone can come up with and solve a problem. This is most problems require a really deep understanding of the issues and research. And we also established 2 research institutes, joint government academic project on storage, energy storage, electrochemical energy storage, and the other one on fusion. We'll not deal with that. Let me skip that. Just this slide shows us the basic of what we want to do is to remove CO2. And in Israel, the dominance of the electricity market is very pronounced, which is a little different than the rest of the world, and our industrial sector is small. So really we concentrate in the mitigation sector on the electricity and transport, and less on the industry at this stage. Of course, as we progress toward 2050 and we need to reach the zero target, then we will tackle the more difficult problems. I will emphasize that our challenges are significant as a country. The grid issue was mentioned in the previous session. In Israel, it's not, at least as difficult as was thought in the previous session. We currently have a 3 to 4 gigawatts transmission grid power capacity, and we need about 4 times that. So we're not twice, as I mentioned before. We need 4 times, and Israel is more densely populated than most countries. It looks almost impossible. And storage, we also need to increase it by a factor of about 100 from what we have today to 2050, because our renewable energy is solar and requires a lot of storage, and we don't have wind. Land requirements in a small country is also difficult for solar energy. So all of this together is a great challenge, which we are just at the beginning of tackling. Carbon capture is, as you can see here on this bottom left-hand side, will be needed clearly, and we are also putting some effort, or starting to put some effort on checking this, and I will concentrate on that. Let me skip this one slide. So I will now go into the carbon capture and storage description of what we are doing right now. We are establishing, in collaboration with Israeli Geological Survey, what we call an energy wing. And this wing will concentrate its work on issues related to energy, and the most prominent one is underground storage. So this has been in the works for quite some time. It's going slower than what I would like, but it's always like that when we try to raise a significant investment, as is needed here. So we will run this together with the Israeli Geological Survey, again in the format that we established with the academia on a research center. So we'll have a joint executive committee where we as a government will influence what research directions of the research and what is going on. And the budget that we hope to allocate to that is over 15 million euros over the next 10 years. We are still not, we have not actually been able to guarantee that at this point. So what is the main thing? I said that we are going to look into underground storage. So there's going to be a characterization of the Israeli underground, more thorough, and also oriented toward storage of various things that we want to store now. That put CO2 at the top. Of course, but other reasons to store underground we are quite clear. We may want to store large amounts of hydrogen, compressed air for electricity storage. We still need to store natural gas, at least for the next 20 years. Now, heat is also something that we could potentially store underground. And also, we are looking into deep underground heat extraction, geothermal energy, usually it's called. And of course, there's, I'm sorry, the word waste was dropped here, but nuclear waste in case Israel eventually will start nuclear power generation, we will need to handle the waste. So all of these topics are interesting, and we need to improve our knowledge base for the underground of Israel. Just briefly, because I saw that most people here understand quite well, methods of CO2 storage. So there is the structural, meaning basically there is a hole or pores, let's say, that the CO2 can be stored in. The next one is solubility, and the next one, mineralization. This graph here shows essentially the time scale that CO2 can be stored on the x-axis. Let's say mineralization is the longest, and solubility is still also quite long. Particularly for Israel, it looks like solubility will be the prime potential for storage. If we look at the Negev, you see on the bottom right here a map of the south of Israel. And this area, which was, at least the current knowledge, is mostly concentrated there. We can see a cut across from west to east, so west on the left-hand side to east. And we can see the Israeli underground. There are water aquifers under the Israeli ground at depth between about 800 meters and 2,500 meters. They're separated here to upper, middle, and lower aquifer. And the water there are brackish water underneath. Again, this shows a mapping of the south of Israel in terms of the middle aquifer in this case. It shows the depth of the aquifer on the right-hand side and the thickness of the this level of the aquifer. And basically, this shows that the potential for storing CO2 as a solution in water is quite significant, and we expect that we will, if necessary, it will be possible to store more than enough, let's say, underground in Israel. So that covers most of, plus or minus our knowledge. As I said, we will improve this knowledge, expand it to cover more precise or more detailed information so that we can actually auction off to the private sector and reach maybe at some point what Jennifer described, these CO2 hubs projects. But I don't expect that to happen in the next few years. It will take us some time, but I hope that by 2030 we will be more settled better in this sense. So we will have at least a pilot of CO2 storage. I do want to talk a little bit about innovation in the area of carbon capture and storage. I'm starting here actually as a country that has natural gas reserves, and I would say that it is a waste not to use the natural gas as long as we don't harm the environment, and I think it is possible. So if we can separate the methane into hydrogen and carbon, then we will be in very good shape. So again, at least for the next 10 to 30 years, that could be a good solution. So this project here shows H2 pyrolysis. It's done at the Tel Aviv University by Brian Rosen. And basically, methane percolates through the catalyst at high temperatures here. And it breaks into hydrogen and carbon. The carbon floats on the metal and can be then separated physically. When we get carbon is, of course, quite a useful material today. And so there should be no problem to find uses for the carbon. And then hydrogen is a clean fuel that does not emit CO2, of course. And very briefly, a list of companies, let's say, and research projects also in quite broad. So like this list mostly wants to show how broad the research efforts are. And I will mention these companies here and the research projects. So Aerovation is a mineralization project where actually with peroxide, they try to get from CO2 minerals. I will mention that mineralization is actually turning one problem to another. Okay, so we have the CO2 gas, which we need to get rid of somehow. And at the output, we get minerals. So most of the minerals, if we think about the quantities that we're talking about, gigatons of CO2, the minerals are not used for these quantities. So we need actually to get rid or at least store them. So these projects need to be done at locations that the minerals can just stay or be piled or something like that. So it's not a negligible issue, serious issue where actually to put the minerals at the end. And another company, Carbon Blue, is attempting is a company to get CO2 from the seawater again. Direct air capture, I have to say, personally, looks quite difficult in terms of quantities because the concentration of the CO2 in the air is so small. So if you look at the numbers of how much air you need to pass through your system, they look quite scary. And of course, the economic numbers don't make any sense right now. However, for seawater, there is, I believe, a lot more potential. There's a lot more CO2 there. And so this company is trying to get carbon from the seawater with a specific catalyst that they develop. Another interesting direction is to store CO2 in algae and then bury the algae in the deep ocean. This needs to be tested also in the environmental sense, I would say. An interesting idea comes from a company called Bonvento. It's a company that says, okay, we have wind turbines running. The wind turbines actually process a huge amount of air. So why don't we put, let's say, or put them to use to do things similar to direct air capture. In this case, they want to capture NO2, which is also a greenhouse gas. So they want to cover the wings of the turbine with a catalyst. And also you need the UV light, so to light this area and then capture the NO2. It is an interesting idea in the sense that the wind turbines process a huge amount of air because of their nature. So that alleviates the necessity, the issue that I mentioned before. How do we get all the air through the system? REAP Air is a direct air capture company with a membrane, special membrane. Levolt is actually doing CCUS, so it's doing, let's say, standard, not any novel technology, but standard carbon capture, and it tries to create from the carbon and separately generated hydrogen, methane fuel, in order to reuse the carbon. We are supporting a project this is also an industrial stage project, carbon storage in wetlands, was also mentioned by Jennifer before, as a potential for CO2 sequestrations. And in the academia, we have a project for mineralization of brine from desalination attempt, and electrochemical selective CO2 reduction to fuels also. So the potential to generate fuels from the CO2 is also quite attractive, as we will need fuels as part of our overall energy scheme for 2050 with zero emissions. That concludes my talk. I thank you, and would love to hear from you if you have any questions or comments. You can also write to me later on. Thanks.
So now we go back to academia and see how we spend the money from the federal ministry. My name is Niklas von der Aßen. I'm from RWTH Aachen University in Germany. If you've not been there, there's a nice drone shot of part of our city. It looks a little bit nicer to the right because that's where we have a nice cathedral. But I like this perspective because in the background, you see one of the dirtiest coal power plants that we have in Europe. So that's still present, but soon to be history. And of course, in the front of the picture, you see our institute. And of course, that's the future. And in the future, we think we will have direct air carbon capture, so what we've heard already. And I would like to ask the question whether that's an energy solution. So we know what's the problem with our energy system right now. It's CO2 emissions, and that's why we rebuild pretty much everything. So if we now add a new technology to the portfolio, the question is, can it actually reduce or remove emissions? And in a nice study by our colleagues on direct air capture of an industrial air capture system by Climeworks, they made a thorough life cycle assessment, and what they showed is that the carbon footprint is negative, so that we actually reduce or remove CO2 from the atmosphere with this technology. So the purpose of the technology is met. That's the good news. However, what you see on the x-axis is the CO2 intensity of electricity. Because this process needs energy, and needs a lot of energy, and this energy has to be clean in order that it makes sense so that we have a net removal of CO2 from the atmosphere. So overall, then this energy is quite huge, and it's additional to all the additional electricity and energy demands that we heard before: direct electrification, electric vehicles, heat pumps, indirect for hydrogen use, and so on. So the question is, what's the place of direct air capture? And what we like to do is to sort things and kind of draw some merit order curves. And that's what my PhD buddy, André Sternbeck, did. For the question, you get 1 megawatt hour of electricity for free. Yeah? What should you do with it in order to reduce as much CO2 as possible? So what should you substitute? And he found some exotic things like making formic acid with electrochemistry, but then the usual suspects are like heat pumps and battery electric vehicles where you save the most. Then you have some other things that still reduce CO2 emissions, but to a lesser extent. And I was quite surprised to find that direct air capture with the energy use is not to the very right end, it's somewhere in the middle. Well, right now we're at the lower bottom, so the bars that you see are ranges, so we're at the bottom range, and we haven't factored in some upstream energy for the materials, but still, it's not completely nonsense to do this, right? So you could argue from this kind of graph, okay, then let's just do business as usual and add carbon capture maybe from the air. Well, that's, of course, just a selection of technology, so that's not the complete picture, because, of course, you can capture CO2 from other sources. So we draw another merit order curve for where should you source the CO2 from, and you can see now it's negative numbers, so also reductions again. There are other sources where you have much larger reductions, so that makes much more sense. And just to the very right end, this gray part, that's direct air capture. So that's kind of the last thing that you should do. So only if we kind of got rid of all the other CO2 sources, then from this energetic and environmental perspective, then we should do direct air capture. So to come up, to answer the question, that was discussed in Nature Communications, is direct air capture an energetically and financially costly distraction? Yeah, maybe to some degree, but it's not total nonsense. But what we can conclude is it's definitely not the first thing that we should do. Maybe it's the last, maybe not. But the thing is, and we heard that already, we have to do it. Yeah, so that's what we know from the different graphs, scenarios, and projections, that by mid-century we need some sort of negative emissions in order to limit the warming between 1.5 degrees. Whether we like it or not, and whether we can achieve the drastic reductions now or we start later, then we need more or less negative emissions, but we need it. Yeah? But we need it, as we heard before, after we did all the reductions. So to make it more catchy, I would say reduce at best and then remove the rest. Yeah? Okay, but removal is necessary and it will be huge. So the scale, I don't know if you remember the small numbers in many of the presentations from EA yesterday and also from Jennifer Wilcox, it will be in the gigaton scale. Yeah, and with the energy demand of gigajoules per ton CO2 removed, we are on this exajoule scale worldwide. That's in the order of magnitude of renewables that we have today. So what does it mean for the development of direct air capture? It means we should be as efficient as possible, yeah? And we have to have it ready by 2050, even earlier, because 2050 is when we should be CO2 net, we have net zero emissions, but we have some hard to abate emissions, so we have to have negative emissions even before that. Not necessarily direct air capture, but we need this technology very soon, so we should really start developing now to have it ready and to have it very efficient. Okay, so we need negative emissions. Maybe just one more word on this, because it's sometimes confusing. Net negative means we have to take CO2 from the atmosphere and store it somewhere else. As Robert Schlögel said, we need a sea dump, yeah, which is not the atmosphere. So, and that's the only way to achieve net negative emissions. You can do carbon capture and storage with fossil carbon and also carbon capture and utilization, but that's at best carbon neutral, which is good, we should do, but it's not helping in the sense of these negative emissions that we also need. And in order to be clear that it's net negative, I think we should do sound environmental assessment, looking at the entire life cycle and also taking into account other environmental impacts, because we know we will have a trade-off. There will be other impacts at the benefit of reducing or removing CO2 from the atmosphere. Okay, so we have a German project called CDR Terra and CDR Mare, where we look at carbon dioxide removal technologies on land and in the ocean. I won't go into the details, so I will focus on direct air capture. Yeah, and the rough classification is what we've already heard into solvent-based technologies, where we absorb into a liquid. It allows a continuous process, but we need high temperatures to get the CO2 out of the solvent again. On the other hand, we have sorbent-based or adsorption-based capture, where CO2 adsorbs onto a porous solid. And the benefit is that we can do the desorption of CO2 from that material at much lower temperatures. The downside is we have a solid, so we cannot just pump it around. We need a kind of adsorption and desorption cycle. And with this, I would like to go a little bit into the details of this technology. So how does it look like? Well, we have a device with some kind of material that likes to adsorb CO2. And then we have a fan and blow air through this device. CO2 is adsorbed onto the surface of this material, and then CO2 pure air comes out again. So then we close the inlet, we evacuate the remaining air, and then we add heat, and we add even more heat, and then the CO2 is released again. Well, why do we distinguish between this first and second heating phase? Well, there are different materials and different concepts, but for the material that we looked at, it does not only like CO2, it also likes water. And there's moisture in the air, so the material absorbs CO2 and water, and we also have to get rid of the water again. And the nice thing about the material we looked at is if you apply heat for desorption, first the water is released, and then after that the CO2, so with the right timing you can kind of skip one separation step afterwards, or the condensation. But they're different concepts. This is the basic idea, and this is what we want to use to kind of optimize the system across different scales. So ideally, we would also design new molecules, materials, have varying process concepts tailored to this. We build some prototypes to validate simulations and then also put it into big energy system models, because energy demand is key, and that also drives, in the end, the net negative performance and also the other environmental impacts. I will just talk about 3 approaches that we wanted to do. So we have a DAC process. How does it look like? So in the middle, there's this plan. That's kind of the process that I showed you before. And this requires energy, and of course, this energy comes with CO2 emissions, even if you renew some renewables. There will also be emissions from constructing the plant and from the sorbent production. There will be energy for compression, storage, and so on. So that's kind of the process that we look like. And what people typically do is they optimize this for minimal energy demand. However, that's not the complete picture, because we have emissions that are not really energy related, like from plant construction and sorbent production. So we thought, okay, how does it look like if we change it and minimize for net CO2 removal? Because that's what this process is supposed to do, remove CO2. So yeah, that's the setup. It kind of is a model for the Climeworks container that you can buy. So now the question is, you bought a container from Climeworks for direct air capture, how should I operate it? And we say operate it with respect to a maximal net CO2 removal, and to skip some of the details we could show in optimization in this Pareto front, because you always have a trade-off with the plant productivity. That in the red curve is the classical approach, but now we have the blue curve optimized for removal, and we get an improvement. It's quite moderate, maybe 4%. So what else could you do? Well, we already heard about siting. So we have this container, where do we put it? Yeah, we could put it in different places of the world, and that affects our process. Firstly, it's affected by ambient air temperature and humidity. Yeah? So cooler temperatures favor the kinetics of adsorption. Humidity is in our material. It favors co-adsorption. It can also be disadvantaged in other materials, but it affects the energy demand and productivity. So, and then we also heard energy is different in different places of the world. We looked at wind and solar PV as energy sources and their carbon footprint, which varies if you have larger wind speeds, higher solar irradiation, of course, then the carbon footprint comes down. So the question is, where should we put it? We first looked at just ideal supply, so we neglected energy demand and just looked at the influence of the air, and this is kind of the result. Blue are good places, so it's in places where it's cold and humid, yeah? But then we find something like a good place that we might have thought of in the beginning, like the Sahara Desert, is not so good. Yeah? But you could add PV panels there. So how does it change the picture? That's the second case. It doesn't change it too much, still not a good place, but the north regions are not so good anymore because simply the sun doesn't shine so often. So what about wind? If we couple it with wind, then we see, just a second, that the good places for direct air capture, where the air is good for the process, and high wind speeds, they kind of overlap. So that's, you can see, for example, here something like Iceland. Yeah, that's where Climeworks put their DAC plants. They don't use wind power, they use geothermal. Could be another case that we haven't looked into yet. For transparency, we completely ignored storage. So we assumed just we capture it. We don't know how to store it, where to store it. So no transport or storage included in here, but of course we can do that. Then one final thing that we looked at and we heard, okay, if we want to reuse renewable energy, we know it's fluctuating. So why should we operate our process in a steady state manner? Yeah, it works, but it's expensive, and can we reduce the cost by adding flexibility in the sense of a demand-side management? Right. So what we did is we added flexibility to the process. How did we do it? This is kind of the process also in a cycle. And what we did is we added breaks before and after the absorption phase, so we can just kind of decide whether we turn off the fan or not and just wait a little bit. And also during absorption, we can kind of adjust the power of the fan, so the mass flow rate of air. And this tiny bit of flexibility is now put into an optimization to reduce the cost or optimize for cost. We compare it to a case where we just have identical cycles over the year, and we end up with a net carbon removal cost in the order of 750 euros per ton of CO2 removed. And if we now operate it flexibly, which is quite challenging from a computational point of view, we have some time series here for prices for the carbon footprint. And to be honest, we also have time series for air humidity and temperature. And if we leverage that by optimization, spare the details here, we end up with individual cycles, so a day cycle, night cycle, summer cycle, winter cycle, and we can reduce the cost by about 27%. So just by adding flexibility and not taking into account that you get any money for the flexibility or what happens to the grid. So next thing we do is to put it in our energy system model that we have and have that combined as well. So that's just 2 PhD students in less than 3 years, who I think did a great job, but there's much, much more to do. We just looked at one material just for the reason because there's not much data available, but we also build up some prototypes and testing equipments. So I think there's lots of potential to even bring down the cost even more, right? But we have to do a lot, and I just listed a lot of challenges that we have. So, yeah, very important is the material. Yeah, we need classification, we need data. They have to be very stable, which they are not so much right now. So if you're working on this or if you have data, please reach out to us. We neglected storage, as I said before. We have a project where we look into, our partners look into acceptance, risk perception, and mental models of DAX, which is quite interesting. And I think we have to find good business cases to really make it work, and the support by the right policies. So if you're working on this, you can contribute, please talk to me. I'm happy to exchange or happy to connect you with our other project partners. Thank you very much.
So what I would like to tell you about is a project that my partner Matthias May and I started or thought about when we were postdocs, and that is now a project investigating negative emission technologies based on photoelectrochemical methods, and I'll present to you the current status of this project. So this is a project with quite a few partners. You'll hear more about that in a minute. First of all, what do I do? I'm a professor of climatology at Tübingen University, a small university town in the south of Germany. It's beautiful. I describe it as, it's like Cambridge in the UK, just with hills. And it's a great place when you're a climate scientist for various reasons, because it gives me peace of mind in my daily life. What you see here is something that my research group is focusing on. Our mission is to think about sustainable pathways under climate variability. You see 66 million years of evolution of the planetary surface temperature. From the hothouse climate, gradual cooling towards future projections based on state-of-the-art Earth system models. And you have in the far right, modern era and the future, these projections run with low, medium, and high mitigation efforts. And when you look at the scale, this is on the far left, I would like to draw your attention to the fact that this is an anomaly. With respect to our observational period, so 1961 to 1990, and the maximum value is 16 degrees. Global mean temperature, warming with respect to the historical period. And over the time that we're looking at here, CO2 concentrations have varied. So the last time we were at CO2 concentrations that we are at today is at least 2 million years ago, might be even now further back in time. And this is a time when we had a different ocean circulation. We did not have established ice sheets, so we had a much higher sea level. And at the same time, this is the kind of phenomena that we have to take into account when we're talking about global warming and thresholds of 1.5 degrees or 2 degrees of warming. So to come back to our mission, we look at what does this kind of warming or cooling do to climate and environmental variability in space and time? Do our models that we run into the future actually give us a realistic depiction of the variability that we could see? And what kind of sustainable future pathways can we envisage? So the second part, really, in devising this project that is NetPEC comes from solar-driven electrochemistry and the solid-state electrochemical expertise of my partner, Matthias May. And just like me, he leads an Eminöter research group at Tübingen University. And here I've brought one of their recent highlights, a new record of solar to hydrogen production on centimeter scales based on 3,5 semiconductors. And I encourage you to check out the references for details. But here you can already see that our perspective is based on climate and on a detailed understanding of processes in climate, as well as a detailed understanding of materials and how they interact with light. So why are we talking about negative carbon emissions? On the x-axis here, we have the cumulative amount of carbon going into the atmosphere, and the y-axis, we have global mean surface temperature, here with respect to 1850 to 1900. And the blue, red, orange scenarios are the same ones that I showed you earlier. But now we've compressed this into timelines with carbon emissions. And the key point that I want to make here is that every single ton that goes into the atmosphere adds to global mean surface temperature, and this is because our natural sinks are slow and they are only adjusted to offsetting natural sources. So decarbonization is key to the 1.5 degree target and to lower the risk of crossing these thresholds that, honestly, we cannot at this point really determine well. The other point that was made earlier as well is that we need, by 2050, the potential to realize 10 gigatons of CO2 removal per year. And this is really exclusively for hard-to-abate emissions. We also, and this is something that in Niklas' presentation, we also saw the potential and the realization of this potential needs to start by the end of this decade. What kind of the approaches are there? And Granger asked me to include a bit on natural photosynthesis. Of course, if you promote a project based on artificial photosynthesis, this is kind of important as well. So the mature technology that is proposed and has been established for a while is based on bioenergy, carbon capture and storage, and it's illustrated in the top left here. But of course, in the public eye and public opinion, a lot of our problems could be solved by afforestation. There is direct air capture, and I will not add to what Niklas said about that. There are approaches such as biochar, soil sequestration, enhanced weathering, as well as different methods applied on the ocean. It's important to note here that most of the mature technologies draw on natural photosynthesis for the fixation of carbon, but there's a really difficult conundrum here. If we still want to be able to feed the planet, then this kind of approach is really difficult to reconcile. Why? Well, let's take a step back and let's appreciate that forests are beautiful. They're important for us, for humans. And at first glance, what we think about artificial photosynthesis brings to mind these difficult environments, such as this solar thermal power plant here on the right-hand side. What is going on in the background is, of course, that shortwave radiation is integrated in the plant and produces carbohydrates, and this is exactly what we aim for also in our NetPEC approach. So to drive the reaction directly with sunlight. So our key benchmark here is the solar to carbon efficiency, so the number of carbon, or the amount of carbon fixed from CO2 of the atmosphere divided by the number of typical photons the solar spectrum provides. If we think about natural photosynthesis, then what we need is about 10 gigatons per year, which translates to 10 million square kilometers. And now we can think about the size of North America. The efficiency for energy concentrated in biomass is in the order of 2 to 3%, and this is, the 2 to 3% is ambitious. It's for genetically modified organisms and not under natural sunlight. Artificial photosynthesis, however, on the other hand, is, and this is something that threw me a lot in the beginning when studying the literature, any kind of small to large modification of natural photosynthesis. So if you scan the literature, there's a lot out there. So that's something to be aware of. Energetic efficiencies can be 20 to 45%. 47% is actually the current world record, but I see Mr. Hebling has left, so I'm safe perhaps with the 40 on the slide. But it's much higher than what natural photosynthesis does. Now, focusing on photoelectrochemistry, and this is the third point, we want to maximize this solar to carbon efficiencies. And when we discussed this first, we realized that we really need to put carbon at the front. So efficient carbon sinks are not necessarily value-added products. And, you're missing a slide here. That's really sad. So on the right-hand side, you would see a diagram that shows you that oxalate formate are really great products in terms of the solar to carbon efficiency, whereas other products which include more hydrogen bonds, such as methane, are far less efficient. And this translates directly, and you can check out the reference on the right-hand side, Earth System Dynamics. This translates directly into the required module area. So on the bottom here, we estimated with conservative 50% of maximum efficiency that only 17,000 square kilometers for 10 gigatons of carbon for oxalate as a sink product would be sufficient. Now, this is completely based on assumptions and theoretical calculations. And within the framework of the NetPEC project, we want to go further. So in this table, I've put together the benchmarking criteria that we've looked at. And we realized there's natural photosynthesis, there's what we try to do in NetPEC, which is artificial photosynthesis and direct integration. And then there's what we can do on the right-hand side, PV and electrochemistry. So energetic efficiency, solar to carbon efficiency, water requirements, costs, the potential for carbon storage all come into play. And at the bottom, I've added beauty and multifunctionality, and I think in particular in public opinion, this is a very important aspect, and this is entirely engineered for most of the solutions that we've discussed in the last days. So what do we want to do? We want to take carbon out of the atmosphere. We start in our project from the concentration of CO2 in an electrolyte. We do not include the direct air capture part. We focus on how we could realize efficient conversion to solid or liquid products. This is important to us, directly solar-driven, solar to carbon efficient, and safe liquid or solid end products. So our project going to jump quite quickly over the details of our project, but you're then welcome to check out the slides later. Integrates a partner in Stuttgart on perovskite solar cells. We need about 3 volts to drive the electrochemical reactions. And of course, in future projects, we might also bridge to other types of solar cells. Second part, and this is the biggest part of the project, is looking into how to characterize at these electrochemical cells that we're aiming for, the reactions that are going on, how to understand them. And we also use, like was just alluded to in the talk by Mr. Friedman, liquid metal catalysts. So these are 3 partners that are particularly focusing on catalysis in Ulm, Tübingen, and in Berlin at the Helmholtz Center. And we look at non-aqueous environments, and in particular the production of formate and oxalate, but also carbon flakes. And on the one hand, yes, we already see these products, formate and oxalate. We can say that, and there should be a picture here in the bottom right, where you could see this shiny surface on the previous slide, here, and you would see it in black on the right-hand side, because we've recently, in the last 2 weeks, been able to confirm that we are actually seeing solid carbon on these surfaces, so our approach works. So we've implemented this in climate models, and we test different spatial scenarios for deployment. On the left-hand side, this would be the picture for the land cover type desert. On the right-hand side, we have one of so-called fair share scenarios. We, in the global north, have been emitters in the past, and we should also be deploying this in the future. This is the kind of assumption. But what is a fair share paradigm? What are realistic areas? This is challenging to define and to discuss. So finally, we do look into storage. And the good news is, for the products that we envisage, graphite, oxalate, organic acids, the type of area that is suitable for solid storage is available. It's in the same order of magnitude if we consider surface mining or oil reservoirs of our current CO2 emissions. And more will be forthcoming in a paper by the partners in Darmstadt. We do see that this entire process is already carbon negative at the current electricity mix, but we realize that the electricity mix is currently constraining us because we do not yet have a fully integrated device, and we have to assume that, for example, our energy at this point comes from photovoltaics, and we do have to drive electrolyzers. And we do need to integrate direct air capture. We know that the integrated device in a mature stage will probably not need a full direct air capture process, but in the figure on the right-hand side, you can see that we do actually see carbon negativity, and the major part of the residual emissions are coming from direct air capture. So we have a couple of challenges ahead. We're only 1.5 years into the project, so I think it's quite encouraging to see. We have challenges at all fronts, but we are quite encouraged to continue with this. So my final take-home message is, I would say, we do see that direct photoelectrochemical reduction can facilitate efficient carbon removal, and efficiency is key if we think about this limited resource that is the land surface. In electrochemistry, we need to include imaging and understanding so that we can control and design the reactions, and modeling is key to that as well. We see that the land and climate impacts from carbon dioxide removal scale with the efficiency. And we do actually see quite a lot of potential for solid and liquid disposals within the national borders, and this is important for the polluters pays principle. Of course, our products can also be used in CCU, but the scale of the problem is too big to only envisage CCU. We, in the project, have benefited from including social, ecological, and economical life cycle analysis, and this is important to ensure that we also include biodiversity, justice, and equity in our future projects and scale up. And it's important to ensure public support, because if people do not understand our technologies, they cannot profit from the technologies, and it's implemented in a top-down manner, they will not support us in scaling up. Finally, I want to say that this is really coming out of fundamental research, and it's now being co-funded, thankfully, by the BMBF. And I would say basic and applied research is required for innovation and for scale-up, and this is not an area, in particular basic research, where a lot of money is going at the moment. And with that, I thank you, and I'm looking forward to questions potentially over lunch.
Thanks a lot for all the presentations. I have a quick question to Niklas, because when I was listening to the stack approach, I thought you have to heat up again to remove the humidity and the CO2. Probably it's, why don't you use it in, let's say, cities like Singapore, where if you do the air conditioning, you have to do the same process step anyhow?
Yeah, so water is a problem, but it can also be good for the process. Yeah, it can favor the process, and then also like the question where you put it. So in the scale that you might need for gigatons of CO2, we think you should put it like somewhere big outside. Yeah, but of course there are a lot of startup companies, also from a business point of view, that integrate it into air conditioning. So that's happening. And also maybe to touch on that also, because the water can also be a byproduct, so if you use that in arid regions, that can also be very advantage. And there's a nice work by Aldo Steinfeld from ETH, who combines direct air capture to provide CO2 and water, and from CO2 and water then make synthetic fuels. So you make fuels just from components out of the air and sunlight. So that's really nice. Which is not
negative. And of course the carbon engineering folks are talking about making fuel. Other questions around the table? Yeah, Jay Abt.
Yeah, also for Niklas, have you done the math to figure out how many terawatt hours the CDR envisioned by 2050 requires?
I have it. I have to look it up. I keep forgetting them. And I also have to say maybe first, I think the 2050 projections have very high uncertainty. So for me, that's always like, I mean, that's just guessing, right? But it's, wait, let me check just for a second.
Well, even the 2035 wedge of the startup.
Sorry, I didn't get that.
Even the wedge startup in 2035 for CDR is significant. I'd be interested in the number of terawatt hours.
Yeah. So my calculations, like with some assumptions that, I mean, you need electricity and heat, and the question is, well, if you can waste heat, that's always perfect, yeah, but if you can, for the low temperature, maybe also use a heat pump, and let's say just 50% is provided by heat pump, good coefficient of performance. For the 2 gigaton scale that was mentioned a couple of times, then you end up with something like 4,000 terawatt hours. Yeah.
Any other questions, comments?
I have one here.
Yeah, go ahead, Yi.
So we saw different number, right? I understand it's far away. Is a 2 gigaton per year CO2 should be looking into, or is a 10 gigaton per year? Let me share my thought with you. I understand it's carbon negative technology get to 2 is to offset by 2050 those still hard abate sectors. But if we could do 10, you use 2 to offset those carbon still emitting, Then the remaining 8 is purely 8 gigaton per year. Taking 8 gigaton out of the air could be very attractive. So every 1 ppm change is about 8 gigaton of CO2. If we continue to do that for 150 years, we are going to take out all of the CO2 from the Industrial Revolution, right? Roughly that's 140 ppm adding to the air since, right before, compared to right before Industrial Revolution. I think that will have huge impact on the climate. It's worth a discussion. Should we be even more ambitious in thinking about that, is taking out the CO2 and get back to the pre-Industrial Revolution? Yeah.
Yeah, and of course the counter-argument you will hear from many is that paying any attention to direct air capture sort of takes attention away from doing what we should do, which is reducing emissions. But that doesn't mean we shouldn't at least be thinking and working on it. But it is politically very touchy. Yes, go ahead.
Thank you. I just wanted to briefly comment. So the 10 gigatons are global, and the 1 gigaton was, I think, mentioned by Jennifer Wilcox in her address, I think is a national
It's US only?
It's US only, so that explains the major difference. So 10 gigatons is what we need at the global scale, just to clarify. And to clarify further, going back to pre-industrial conditions would not be a bad idea. Whether it's feasible or not, that we can discuss later.
Okay, well, seeing no other questions or comments, I'm going to wrap this session up with just 3 slides on a key issue that we haven't been talking about. That's not an energy issue, but very much a climate issue. There are basically 2 ways to change the climate. The first is slow. That is, we can warm the Earth by gradually adding more greenhouse gases. We can remove carbon dioxide from the atmosphere, and that's a slow process also. Or we can modify albedo. Now, nobody is proposing, nobody with his head screwed on straight is proposing that we ought to be doing that right now. On the other hand, in our institute for a number of years, we have thought a little bit about the political and other implications of this. We actually, back in 2009, we discovered that the international community didn't, the political community, the foreign affairs community, didn't even know this was a possibility, so we ran a workshop to begin to get them informed. We and others have done a fair amount of science. Here's a piece that I published in an opinion piece some years ago, and the key point here is that solar radiation management has 3 essential characteristics. It's cheap, fast, and imperfect. All right, the fact that it's cheap means it's tempting. And the fact that it doesn't take consensus means that some major entity like China, for example, could wake up one day, decide it's hard to feed our people, and do it unilaterally. So none of this is to argue that we should be doing it. It is to, however, argue that we need to understand it. If we don't understand it and somebody suddenly decides to do it, we're in a deep problem. So here's a couple of pieces of my own on needing research guidelines. The National Academy, the U.S. National Academy has similarly been working for some years to try to improve understanding. Jennifer Wilcox referred to one of a pair of reports back in 2015. The other one on that pair was on albedo modification. Much more recently, just in 2021, the National Academy did another review of albedo modification. Finally, after a couple of decades of difficulty, the NSF has indicated they will now support, in modest ways, some research in this area, and the University of Chicago has just announced that it's building a brand new program on advancing our understanding of the potential risks and benefits of climate system engineering. I say all of that not as a proponent of doing any of these things, but simply to remind us it's another thing out there, it's cheap, and it's tempting. And so we do need to understand it. And with that, why don't we go downstairs and have some lunch?
Can I make a comment on this?
Sorry,
Of course, of course.
No. We have something from the internet. Sorry, we didn't see you for a second. So Dan has something to say.
Yes, please.
So, yeah, I don't want to go to the rest of the session. Just one technical comment on the discussion on the carbon budget. I think there was some confusion about using gigaton of carbon and gigaton of CO2. Yes. And I think we have to pay attention to the difference. It's a factor of 4. Yeah. But regarding the albedo, I want to say that when you talk about albedo and geoengineering of sun solar reflection, you probably mean engineering at the top of the atmosphere, of adding aerosols. But this is very dangerous because we have no control. It's difficult to reverse it. But there are also ways to manipulate the albedo at the surface of the Earth, and this is something that get less attention, but can be as efficient and easier to do, and it's actually considered in some areas. Even I hear that in plant genetics, breeders are trying to change the color of large-scale crops to help modify the albedo of the surface of the Earth. This is a much safer approach to modifying global albedo.
Field, there is a lot of work on not just stratospheric activity, but things like coastal clouds, seeding clouds with seawater, changing surface albedo in a variety of ways. I was not, because I wanted to be very brief, the key point is just that this is an issue we should not forget about.